Hey guys, welcome back to Mr. Aparicio's geometry course. Today we're going over section 2.4, which is all about algebraic reasoning. We need to make sure that we're able to solve and complete algebra proofs. Let's get into it. We're going to use algebraic reasoning to solve algebra proofs. And algebraic reasonings is just the ability to recognize and to explain or to describe the patterns and processes that are required to solve algebra equations. So I have an example of that over here. We have this equation. If x plus 2 equals 8, then x equals 6. We know that to be true. If we plug the 6 in for x, 6 plus 2 equals 8. The specific algebra that we would do, though, x plus 2 equals 8, to get x alone would be to subtract both sides of the equal sign by 2. We end up with x equals 6. So to fill in our blank here to the right, isolating x requires subtracting both sides of the equation by 2, as I showed you up here. So this is algebraic reasoning. It's not just writing x plus 2 and then writing x equals 6. It's explaining that we had to subtract both sides of the equal sign by 2 to get our 6. We know that to solve algebraic equations, we're going to have to add and subtract and multiply and divide, sometimes square root. We're going to be performing all of these functions to solve for variables in algebra problems. When we're doing algebra proofs, we're going to use the same functions as properties of equality in order to explain how we solve for a variable in a given algebra problem. For all these examples that I'm going to be showing you, all these properties of equality, I'm going to use the letters A, B, and C. And those are just going to represent any real numbers. So if I know that A equals B, A and B are the same value, then if I add the same number to both sides of the equal sign, I will get an equal result on either side. So if I add C to A, but I also add C to B, this will still be a true equation. They'll still both be equal to each other. Give you a better sense of this if I use actual numbers. If A is 10, and A is equal to B, then B is also 10. 10 equals 10. If C is 2, and I add it to both sides of the equal sign, I still get a true equation, a true statement. 10 plus 2 equals 10 plus 2. That's true. 12 equals 12. All right? Here's an even better example to get you understanding. And before I actually do this, I made a little error here. This wouldn't actually be 20 in this problem. If x minus 10 equals 15, and we do the algebra here to get x alone, we would have to add 10 to both sides of the equal sign. We would actually get 25 for x. Sorry about that little error there. But what we did is we added the same number to both sides of the equal sign. That's exactly what we just described. That is the addition property of equality. And I'm just gonna abbreviate as I go through here. Our first example here is asking us to spot the equation that would require the addition property of equality in order to solve. All right, now what we don't want to do is just look at equations that have plus signs in them. Because remember, the addition property of equality is when we add the same number to both sides of the equal sign. So just because there's a plus 12 here doesn't mean the addition property is involved, because there's not also a plus 12 on this side of the equal sign. Instead, what I'm going to do is I'm just going to show you the correct answer and explain where that addition property comes up. And it happens in this equation right here, C. We have 2 times x minus 4 equals 12. Well, if I distribute the 2 into the parentheses, I'm going to end up with 2x minus 8 equals 12. And to get that 2x alone, I will have to use that addition property of equality to move the negative 8 to the other side of the equal sign by adding both sides by the same value. That's our addition property of equality. That only happens in C. Again, not in options like D. That's adding, sure, but we're not adding the same numbers to both sides of the equal sign like we had to in this algebra. So the correct answer here is C, using our addition property of equality. The subtraction property of equality is very similar to the addition property. We're just subtracting instead of adding to both sides. So again, if I'm using A, B, and C as real numbers, if A equals B, I can subtract both sides of the equal sign by the same value, and I'll still yield equal results. So I could subtract the left side by C, and that would be equal to the right side being subtracted by C. To see how that actually occurs in algebra, we can look at this conditional statement here. If x plus 7 equals 10, then x equals 3. How do we know x is 3? Because algebra would require us to subtract both sides of the equal sign by 7. That would cancel the 7's here. I'd have just x equaling 10 minus 7, which is 3. So again, the reason that this is true is because of the subtraction property of equality. Our next example asks us to identify which equation would require the subtraction property of equality to solve, and we have several correct answers here in this example, right? A, B, and D would all require us to subtract in order to solve. So we look at A, that's pretty straightforward. To get that 3x alone on the left side of the equal sign, we would have to subtract both sides by 15, subtraction property of equality. The same kind of thing would happen in equation B. After distributing the 2, I would get 2x plus 16 equals 32. And to get the 2x alone, I would have to subtract both sides by 16. That's our subtraction property. Right? For D, after combining the 7 and 17 as like terms, we would get x over 5 plus 24 equals 20. And again, to get the x over 5 alone, I would have to subtract both sides by 24. So A, B, and D all require the subtraction property of equality. I'm sure you're catching on here. Our multiplication property of equality requires multiplying both sides of the equal sign by the same term. So again, if I know that A equals B, I can multiply both sides by C, and I'll still yield equal results. So A times C, which would just be written as AC, would equal B times C, which would be written as BC. Right, in algebra, we're going to have division involved in our equation in order to get the multiplication property of equality. So we see that here with this fraction, x divided by 7 equals 5. Well, the algebra that we would do here to get x by itself would be to multiply both sides of the equal sign by 7. That's the opposite of what's happening to x here. The opposite of dividing by 7 is multiplying by 7. So again, we have to do that to both sides of the equal sign. That cancels the 7's, and you get 5 times 7, that gives me x equals 35. So again, the reason x would be 35 is because of that multiplication property of equality. Again, we're going to try to identify where that property would be used in an equation. We're trying to find the multiplication property of equality. We have 4 options to choose from. And again, we don't want to just find where multiplication occurs. Like, we have to multiply in B and C in order to distribute the 2 and the 5. But remember, it's what we do to both sides of the equal sign that allows us to explain our algebraic reasoning. So option D is where this is going to happen. After we combine the 7 and the 17, we end up with x over 5 plus 24 equals 20. We would then use the subtraction property of equality to move the 24 over. So we get x over 5 equals negative 4. And then from here, we would use the multiplication property of equality to get x by itself. We would multiply both sides of the equal sign by the same number. Multiply both sides by 5. I kind of wrote that funky over here. It should be this in parentheses. Multiplying both sides by 5. 5's cancel on the left, leaving us with x equals negative 20. Next up, we have the division property of equality, which is dividing both sides of the equal sign by the same term. So again, if we know that A equals B, I can divide both sides by C and still yield equal results. So A divided by C would still equal B divided by C. Right? In our algebra equation over here, we'll get a better example of that. If 4x equals 32, then x equals 8. Let's think about the algebra. 4x equals 32. To get x alone, we need to do the opposite of what's happening to it. So the opposite of multiplying it by 4 would be dividing by 4. And we would do that to both sides of the equal sign. So the 4's cancel on the left, giving me x equals 8. So again, the reason x is 8 is because of the division property of equality. Hopefully you're catching on here. We're just formally explaining the algebra that we're doing to solve for a variable. Again, we're going to identify where our property is going to show up in these equations. So we're finding the division property of equality where we divide both sides by the same number. That's going to happen in these 3 equations here, E, F, and G. It's not happening in H. So let me show you the proof of that. So we look at equation E, we get 3x plus 15 equals 24. To get 3x alone, I'm going to have to use the subtraction property, subtract both sides by 15. I'll get 3x equals 9. From here, to get x by itself, I would have to divide both sides of the equal sign by 3. to get x equals 3. That same thing will happen in f. After we distribute that 2 into the parentheses, I would get 2x plus 16 equals 32. I would subtract both sides by 16 to get 2x equals 16, and then I would divide both sides by 2. That's my division property of equality to get x equals 8. And again, that same thing happens in G. We have distributing our 5, we get 5x minus 20 equals 15. I would use the addition property of equality to add 20 to both sides of the equal sign so that I get 5x equals 35. And now I would use the division property of equality, divide both sides of the equal sign by 5 to get x equals 7. We would not end up dividing at all for equation H. That would require the multiplication property of equality to get rid of that over 5 there. I made a little mistake here and included the distributive property of equality, which is not actually a thing that exists, because when we distribute in algebra, we don't do it to both sides of the equal sign. We only do it to where a parentheses occurs. So there's no distributive property of equality, but there is still, using reasoning, distribution that happens in algebra. For example, as we look at this thing down here, this example, when I want to solve for j and k, I have to distribute the 2 and the 5 into the parentheses. So my explanation of how I solve for x requires use of the distributive property. It's just not the distributive property of equality because it doesn't happen to both sides of the equal sign. So what we're going to do with all these terms now is complete a proof. So proof is when we're given a problem and the solution to the problem, and we have to explain why the solution works for the problem that we're given. For algebra, we're going to have equations. So we have this equation given to us, 3x plus 2 equals 23 minus 4x. We have several lines of algebra that end in the answer for this equation, which is that x equals 3. And we are going to use our properties of equality to explain why each step of the way here is a true statement. Okay, so 3x plus 2 equals 23 minus 4x. Well, the only reason that is true is because it's been provided for us. So what we would say here in our reasoning is that this equation was given to us. Right? That's typically how most proofs will start. The first statement that's true is true because it's given to you. Our next statement says 7x plus 2 equals 23. So we have to figure out what happened from step 1 to step 2. How did we get from this equation to this equation, right? And the way that we did this is by moving this negative 4x to the left side of the equal sign. And the way that is accomplished is by adding 4x to both sides. Hopefully you recall that is the addition property of equality. So the reason this statement is true is because of the addition property of equality. From there, we go to 7x equals 21. So again, what did we do from this line of algebra to get here? And what we did is we moved this 2 to the other side of the equal sign. And the way that would be done, since it's changing sides, would be subtracting 2 from both sides of the equal sign. So the reason 7x equals 21 is because of the subtraction property of equality. And then it brings us to our last statement, where x equals 3. The reason it equals 3 is because we moved this 7 to the other side of the equal sign by dividing both sides by 7. That is our division property of equality. So again, an algebra proof is formally explaining why every step of the way is true, leading to our solution to a problem. Let's do this one more time with a bit of a more complicated problem here. We have 4 times x minus 9 divided by 2 plus 2 equals negative 18. The reason that equation is true is because it was given to us. From there, we're looking at how our equation changed to our second line of algebra, and we notice that the plus 2 isn't here anymore. So that means it's moved to the other side of the equal sign, and the way that would happen is by subtracting both sides of the equal sign by 2. That's how we get to this point. So the reason this statement is true is because of the subtraction property of equality. All right, hopefully you're catching on. That's how this works, of how we give a reason for every step of the way. All right, then we look at what's different from 2 to 3. Well, we notice the parentheses is gone. So that means we've distributed The 4, we did 4 times x to get the 4x, 4 times negative 9 to get the negative 36. So that is our distributive property. Distributive property. Not the distributive property of equality, because I didn't do it to both sides of the equal sign, right? I only distributed over here where the parentheses was. So again, now we're looking at how did we change from 3 to 4. Well, the divided by 2 is not there anymore. So that's been moved to the other side. Remember, the algebra here would require us to multiply both sides of the equal sign by 2. That's how the 2's cancel on the left and they're not there anymore. So that is the multiplication property of equality. All right, now we're on to the difference from 4 and 5. What changed from equation 4 to equation 5? Well, the negative 36 isn't there anymore. It had to have been moved to the right side of the equal sign. And we would accomplish that by adding 36 to both sides. So the reason 4x equals negative 4 is because of the addition property of equality. All right, then we go from 4x equals negative 4 to x equals negative 1. So the reason this is true now is because of what changed with our 4 here, which is dividing both sides by 4. That negative 4 divided by 4 gives us negative 1, so x equals negative 1 because of the division property of equality. So as we do these proofs, it's a good way to think of it. We're thinking this statement is true because of this reason. It always ties back into what changed between one statement to the next. All right, guys, that completes our video lesson for section 2.4 on algebraic reasoning. Remember, there's a section here in your packet to ask down any questions that you want to ask me in person. I'll see you in the next one where we go over geometry proofs. Bye, guys.